This is a revision video for P6b Potential dividers, LDRs, thermistors and resistors. We'll start this revision section on resistors. This diagram shows a simple series circuit where the current flows through one component and then the next component and then the next component. In a series circuit, if you add more resistors, the total resistance of the circuit increases. The formula you will use to work out the total resistance is R equals R1 plus R2 plus R3 plus R4 and so on for however many resistors you've got in your circuit. In this example, we've got 5 resistors that are linked in series. Each of them has got a resistance of 12 ohms. So the total resistance of the circuit, or R, will be 12 add 12 add 12 add 12 add 12, which is 60 ohms. So if you have resistors that are in series, they will increase the resistance of the circuit. Resistors can also be connected in parallel in a circuit. This means there is more than one way for the current to flow around the circuit, as shown in the diagram. Connecting resistors in parallel reduces the total resistance of the circuit for every one you add. Here is the equation for resistors in parallel. You've got 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5 and etc. for how many resistors you have that are connected in parallel. Okay, so in this example, we've got 3 resistors in parallel. One's 5 ohms, one's 7 ohms and one's 9 ohms. The total resistance, or 1 over RT, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. 1 over RT equals 1 over 5 plus 1 over 7 plus 1 over 9. This is equal to 0.454. However, that's not the answer. Don't forget, that is equal to 1 over RT. So in order to get RT, you need to do 1 over 0.454, and that gives us a resistance of 2.2 ohms. Notice that this is lower than any of our resistors. This is a potential divider circuit. In a series circuit, the current flowing in the circuit is the same everywhere, and the total voltage is shared between the components in proportion to their resistances. In a potential divider circuit, the same current flows through both resistors. If the two resistors have got the same value, then the voltage across each resistor is the same, or is divided equally between them. The voltage across either resistor, here and here, and here and here, can be used as an output for other circuits. If we change one of the resistors to a variable resistor, like this one here in R2, then we can change the resistance, so therefore we can change the voltage out across that resistor as we require. The output voltage depends on the share of the total voltage between the two resistors. The total resistance, because the resistors are connected in series, is R1 plus R2. You can calculate V out using ratios. If V in is 40 volts, R1 is 20 ohms and R2 is 20 ohms, what will V out be? So here we have that both resistors are equal. And if both resistors are equal, then the voltage will split equally between them. So this will give us 20 volts and 20 volts over each resistor. Sometimes it's a little bit more complicated than this, as the resistors are not always equal. In this example, R1 is 20 ohms and R2 is 40 ohms. Now R2 is twice the size of R1, so it will have twice the voltage across it. If we want to calculate the voltage across R1 and R2, we can do it by using ratios. So if we look at the problem, R1 is 20 ohms and R2 is 40 ohms. We can simplify that down to 2 to 4 and then 1 to 2. So the voltage will split to the ratio of 1 to 2. So altogether there we have got 3 divided by 12 divided by 3, that equals to 4. Then that means here I've got 1 times 4, which is 4, and then 2 times 4, which is 8. So resistor 1 is 4 volts and resistor 2 is 8 volts. If resistor 2 is much greater than resistor 1, then it means that practically all of the V in is across R2, and the output voltage will be approximately equal to the input voltage. If you think about that the other way around, if R2 is much smaller than R1, then it means the voltage across it is practically zero, and or pretty much all of the voltage goes across resistor 1. This means that the output voltage will be approximately 0. Okay, so here's a question for you to try. I want you to stop the video and see if you can prove that V out is 20 volts. Okay, now we're going to talk about different components that we can add into our circuits. This one here is an LDR, or a light dependent resistor. It's a special type of resistor, and its resistance changes as the intensity of light falling on it changes. When the light levels are low, the resistance of an LDR is high. This is because in an LDR, the outer electrons of the atoms are bound weakly. When bright light shines on them, the resistance is much lower. This is because the light energy is transferred to the outer electrons, and that can allow them to break free. And you should remember that the flow of electrons is equal to the current. And if you've got more current flowing, then you will have less resistance. The graph of light intensity and resistance for an LDR will always give you this shape. So it's showing us that as light intensity increases, the resistance decreases. And that's because more electrons can break free from their atoms, and then they can flow around to carry the current. This property of LDRs can be very useful to us. It can be used as a switch. For example, it could be used to switch on security lights when it gets dark. The security light would depend on a circuit like this. If you replaced R2 with an LDR, then the output voltage would then depend on the light conditions. In low light, the resistance of the LDR will be higher compared to R1, so the voltage across it will be higher and the output voltage is higher. So that means that here we could have a security light connected, and when the voltage across it is high, it will turn on. However, in bright light, so through the daytime, the resistance of the LDR is lower compared to R1. So that means the voltage across it is lower and the output voltage is lower. That means there may not be enough voltage to turn the light on, so it will be off during the day when the light intensity is high. This is another special type of resistor. It's a thermistor. In this component, its resistance changes as the temperature changes. When the temperature of the thermistor is low, its resistance is high. This is because the thermistor is made of a material which does not conduct electricity well at low temperatures. The outer electrons are loosely bound to the atoms, and they are not free to flow through the thermistor. As the temperature increases, more outer electrons gain enough energy to break free from the atoms. And again, it's the electrons that are flowing round that are the current, So if we have more of those electrons, we've got a bigger current and less resistance. The graph of temperature and resistance is the same shape as with the LDR. We've got a high resistance at low temperatures and a low resistance at high temperatures. And again, you can replace R2 in the potential divider circuit with a thermistor. This would then mean that the output voltage depends on temperature. At low temperatures, the resistance of the thermistor is higher compared to R1, so the voltage across it will be higher, and the output voltage will be higher. This could be useful, as in this circuit, we could have a heater connected, for example, so that when the temperature got low enough, the voltage out would be high and the heater would come on. At high temperatures, however, when the resistance of the thermistor is low compared to R1, the voltage across it is lower. So this voltage would not be high enough to turn the heater on. So at high temperatures, the heater would remain off. Okay, so that brings an end to our revision section on potential dividers, LDRs, thermistors and resistors. You can stop the video now and have a go at these graded questions.